Good afternoon and welcome to my seminar. My name is Bryson Marks and today I'll be talking to you guys about the research that I've conducted here at CMU for the past 2 semesters under the advisement of Dr. Hosterman. Now, this research entails the calibration of a Jarrel-Ash spectrograph. So a little overview: what is spectroscopy, motivation behind my project, the equipment and the mechanical issues associated with that equipment, general overview on how I optimize the optics, the data analysis portion, how I got the data, and how I analyze the data. I will conclude and then talk about my future work. So we've all seen this album artwork out there before. This album artwork isn't just associated with good music, it is also associated with the nature of spectroscopy. Well, we have white light coming into the prism. It will refract, travel through the prism, and refract again. But when it refracts as it exits the prism, it'll disperse into its individual wavelengths. So spectroscopy is the branch of science that studies the interaction between light and matter in the form of electromagnetic radiation. In the 1600s or late 1600s, Isaac Newton performed a crude analysis of light from the sun and was the first person to coin the term spectrum. So, chemists also use spectroscopy to identify molecules of interest. Physicists use spectroscopy to understand the properties of materials of interest. Now, a little bit of motivation. Well, I wanted a project that contained a mixture of experimental and theoretical instead of just purely theoretical. I also wanted a deeper understanding into the nature of spectroscopy. And I also wanted to utilize the spectrograph that was donated to CMU by a man named Chuck Birch, as well as the QHY CCD camera that was donated to CMU by the Grand Mesa Observatory. And also in my advanced lab class, I used a more complex system or a more advanced system to analyze the hydrogen deuterium spectrum. And using this project made me realize that it would give me an introduction or a brief understanding into more complex or advanced spectrometers. So a little bit of the equipment involved. Well, on the left here we have a spectral tube power supply with a spectral tube that contains a specific element. Well, when you excite the element inside of the spectral tube, it'll emit light with specific wavelengths. And the bulbs that I used were the mercury bulb, the sodium bulb, and the neon bulb, due to their wavelengths being well known. And we also have this QHY9 8.3 megapixel CCD or charge coupled device sensor. And how the sensor works is photons will enter this sensor through the entry portion here. They'll make contact with the detector that is inside and deposit a charge. That charge is then converted to an intensity value at that pixel location. So, modern spectrometers have this configuration or similar configurations. Well, if you look at this cartoon, we have a source that emits light that will travel towards the lens. It will refract in the lens and then become focused on the entry slit. The light will then disperse outwards from the entry slit towards the first mirror. The mirror will then shine that light towards the diffraction grating. That light will then travel from the diffraction grating to the second mirror. The second mirror will then focus the light on the detector, and this is what creates an image of the the image of the light on the detector. So our Jarrel-Ash spectrograph has these optical components here. If you look on the bottom left, we have an entry slit. The middle left, we have the diffraction grating. And at the top left, we have the QHY CCD detector. And on the far right, we have our mirror. Now, it's important to note that this mirror here has 2 subsections, which I'll go into later. Now, the Jarrel-Ash spectrograph on the bottom has the mechanical components or the configuration like so, where we have the motor on the right bottom. We have the high-low shift function here that enables you to change between high or low speeds. We have a transmission system as well that is attached to the high-low function. This transmission system enables you to switch between different scan speeds in either high or low, depending on which portion of the high-low function you are using. Well, this transmission system is attached to this lead screw here. This lead screw contains a mechanism that is attached to the torque arm. And as this mechanism travels up the lead screw or down the lead screw, it will enable the torque arm to change the angle of the diffraction grating in the previous picture. Now the Jarrel-Ash spectrograph has knobs and a dial on the side. Well, this knob on the left allows you to rotate your diffraction grating either clockwise or counterclockwise. This limit scan light will engage when you have reached the far ends of that lead screw with that lead screw mechanism. Now the dial in the middle here, before it probably had something that enabled it to correspond to wavelength, but right now it only corresponds to the position of the mechanism on the lead screw. And on the middle right here we have the scan speed knob. Now this scan speed knob is attached to the transmission and enables you to change between 4 different speed settings of the high-low shift function. And that's where this high-low shift function knob is. And you can pull that in, you can pull that out or have it pushed in to change between high or low. So now that we understand the equipment that is involved, here is the configuration of the optics inside. Well, the spectrometer being used has the Ebert-Fasty configuration, and the Ebert-Fasty configuration is unique due to one mirror being used to function as 2. If you remember previously, I said that there was 2 sections of that mirror, and this is why. Well, the source here will give off light. It will then travel towards the lens, refract, and focus towards the entry slit. Once the light travels through the entry slit, it will disperse outwards towards the first subsection portion of the mirror. It will then travel towards the diffraction grating. Now, once it travels towards the diffraction grating, it will travel to the second subsection portion of the mirror. And once it makes contact with the second subsection portion of the mirror, it will then focus the light towards the detector. So, we need to check the light path as it arrives on the detector to make sure there is no obstructions and the light travels exactly as it should behave. Well, as the light travels through the entry slit, hits the first subsection portion of the mirror, it will become collimated. And what do I mean by collimated? It means that the light rays are parallel with each other as they travel towards the diffraction grating. Now they'll travel towards the diffraction grating and split into its individual wavelengths, but remain collimated as it travels towards the second portion of the mirror, or the second subsection portion of the mirror. Once it makes contact with the second portion of the mirror, the light will be focused towards the detector. Now, light collimation enables for easy calculation of the focal length of the spectrometer. Now, the focal length of the spectrometer is the length required for the light rays to be focused at a point. Now, imagine focusing parallel light rays from the sun through a magnifying glass at a point. Now, due to the sun being significantly far away from the lens to the focal point, we consider the focal point of the lens to be the distance between the lens to the point of focus. Now, to calculate the focal length, the following equation is used here, where we have 1 over s plus 1 over s prime is equal to 1 over f, the focal length. Now, s is the object distance, s prime is the image distance. Now, if you look at this cartoon here, we have a light source, a lens, and an entry slit. The distance between the light source to the lens is the object distance, and the distance between the lens to the point of focus, or the entry slit, is the image distance. Now, if the object distance is much greater than the image distance, then By equation 1, we can state that the image distance is the focal length. But for us, we need to find the circle of least confusion, or the focal plane that contains the circle of least confusion. Now, the circle of least confusion is the minimal cross-section of a bunch of rays that do not converge at a point. Now, this cross-section is the point with the highest resolution or the most crisp image of the spectral lines that we are trying to find. Well, due to the spherical shape of our mirror, this mirror will introduce the spherical aberration, and that is because the light rays do not converge at a point. Now, it also introduces coma into our optics, and that means that the curvature in the subsection of the mirror will shift these rays slightly. Now, if you look at the cartoon, we see that the outer ray comes off at an angle phi, where the center ray will come off at an angle theta. Now, this just means that theta is not equal to phi, and this asymmetry is due to the single mirror acting as two mirrors. This is also due to imaging off of our optical axis, due to the subsections of the mirror not being in the center of the mirror. And this introduces coma aberration and potentially distorts our image. So coma aberration has the potential to turn a point source of light into a cone. And what I mean by that, if you look at the picture on the right, we have a point source of light without coma. And on the left, we have a point source of light with coma. And this will lead to distortion in our spectral lines or asymmetry in our peaks, which I will get into later in the data analysis portion. So we have a diffraction grating. Well, this diffraction grating splits light up similar to a prism splitting up light. And it allows the spectrometer to see individual wavelengths. Well, something that we need to see or need to be reminded of is that the light that is being imaged is focused on the detector, and this cartoon just shows that it disperses our wavelengths out and why we need our diffraction grating to rotate so that we can see other wavelengths of that light in question. Now, our diffraction grating that is being used is a plane reflective diffraction grating, where we have an incident of light coming in, reflecting off the diffracted light, as in this cartoon here. Well, for the angle of diffraction, the following equation 9 is used, where we have n lambda is equal to d sine of theta. Now, this equation states that n lambda is an integer times the wavelength, and d sine of theta is the path length of light. And this lets us know that the path length of light is just an integer multiple of that wavelength, where n is the diffraction order, lambda is the wavelength of light, d is the groove spacing. Now, we need to note something here, that d is inversely proportional to the number of grooves, which I will call L. So if you increase the number of grooves on your diffraction grating, then the spacing between those grooves will get smaller. Now, the thing of interest in equation 4 is theta, how wide our dispersion will be. Well, rearranging equation 4 for theta yields equation 6, where we see here we have n lambda over d on the inside the inverse sign. Well, this is important because if you increase the number of grooves, our d will get smaller. Well, the d on the inside of this fraction term, if it gets smaller, it leads to an increase of theta. So, without the knowledge of the machine, an inspection process is needed. So we will first look into the mechanical portion, and then we'll look into the optical portion. So the mechanical issues involved, to find these issues, I decided to operate the machine without having any light shone through it, so I could just get a feel for how the machine operates or how the components work. Well, I found an issue with the scan speed dry shaft gear assembly, and I found another apparent issue with the high-low shift function. Well, the scan speed driveshaft gear assembly contained issues on the insides of the gears. This required taking apart this assembly here and analyzing the gears and the driveshaft associated with it. Well, abrasions were found on the insides of the gears, on the inner diameter, if you will. Well, to realize what happened, we have to understand how it comes together. Well, this key fits inside this driveshaft keyway that is on the driveshaft. Well, once the key is inside the driveshaft, then you can put the gears on the driveshaft. Well, due to having 4 gears, you can change between the different gears by having this key enter this notch here. And I will select that gear and use that one to rotate. What I think happened is somebody was running this machine while the motor was on and tried to change the speed without turning off the motor or cutting the power to the motor completely. Well, this introduced the option to have material removed from the insides of this gear at the keyway portion or the key portion of the gear. This material then got lodged on the inner diameter of this gear and the outer diameter of the driveshaft here. Well, this introduced abrasions as they tried to change speeds more and more. Well, this actually led to a difficulty in being able to change those speeds. So what I did is I took some fine grit automotive sandpaper and decided to file down the abrasions on the insides of the gears. Well, I decided to only do a couple of rotations at a time so that I didn't remove too much material, but I would make sure that the abrasions were gone. Well, filing down those small portions on the insides of the gears did remove the abrasions, so I put the assembly back together and then decided to look at the high-low shift function. Well, the issue with the high-low shift knob contains a dead zone. Well, this dead zone is introduced because this gear on the top of this high-low shift function should be connected to the gear here on the transmission. Well, if you lift it up only slightly, you can disconnect this bottom gear on the high-low shift function from the bottom gear on the driveshaft gear assembly. Well, you can also make it to where this top gear is not connected to this gear at the same time. Well, that enables you from disconnecting the motor from the driveshaft gear assembly. And this allows you to run the actual dial by hand or the scan speed knob by hand. Now, this enables the manual rotation of the diffraction grating. Well, this dead zone or the manual rotation of the diffraction grating introduces an inaccuracy or inconsistent readings within the dial. So I had to decide whether or not to remove this dead zone. Well, to remove this dead zone, I needed to place spacers at the top of this high-low shift function. Well, placing spacers at the top of that high-low shift function did in fact fix the issue with the dead zone, but it also removed the low shift function. So now we are only able to use the high speed setting of the high-low function. Well, now that we have the mechanical issues figured out, we need to look at the optical portion of the spectrometer. I needed to check the optical portion of the spectrometer with a flashlight to ensure that the light traveled through the spectrometer and arrived on the detector without any obstructions. Well, this enables me to see how the light behaves as it travels between the diffraction grating and the mirror, as well as it enables me to see how the light is focused on the detector. This will enable me to see how I can calculate the focal length. Well, for the Jarrel-Ash spectrograph, finding the focal length contains 2 parts. First, I needed to find the focal length of the small lens that focuses light onto the entry slit. Second, I needed to find the focal length of the optics within the spectrometer. Now, due to the configuration of the Ebert-Fasti, I am able to use the distance between the mirror and the entry slit as the focal length of the spectrometer, and I am able to use the Now for the focal length of the lens, I'm able to use the image distance of the lens, because the bulb, if you remember, the distance between the bulb to the lens is the object distance, and the distance between the lens and the entry slit is the image distance. Now, due to the bulb being significantly far away from the lens, I am able to use the image distance as the actual focal length of the lens. So I calculated the focal length of the lens to be 19 millimeters and the focal length of the spectrometer to be 0.5 meters. Now I can use this focal length to calculate something called the F number. This F number is the ratio of the focal length over the diameter of the aperture, and it signifies the light capturing abilities of the spectrometer and the lens. Well, like I said earlier, this F number is the focal length over the diameter, so I need the focal lengths as well as the diameter. Now the lens diameter is 22.93 millimeters, and the diameter of the mirror is 7.5 centimeters. Well, using that with the focal lengths from the previous slide, I calculated the F numbers to be the F number of the lens, 0.83, and the F number of the spectrometer to be 6.6. Now, we want these two to match, and it is important that they match, because if they don't, then we have two possible scenarios. Either we have the one on the left here, which is overfilled, where we waste light coming off of the bulb or light from the spectral line not being used. We also have underfilled, where we are not using all of the pixels that we can. So to match these two F numbers, this would signify that the spectral lines are completely filled on the pixels, or the spectral lines will fill the spot on the pixels to a point where we maximize the efficiency. There's no light wasted, and there's no pixels that are not being used. So to find these spectral lines, I use the CCD camera with the EasyCap program and came to this following image here. Well, you see here we have an example of the blue spectral line. Now, how did I know that this is the blue spectral line? Well, I removed the CCD camera so that I could see the actual color of these spectral lines, and did double check that with my eyes. So now that we are able to find spectral lines, we need to look for spectral lines at the opposing ends of the machine's reach. Now this lets us know the viewing limit of our spectrometer. Now, running this machine, I found out that there is a viewing limit of 400 nanometers to 630 nanometers. It is the viewing limit of 400 nanometers to 630 nanometers of the visible spectrum. Now the torque arm, like I said earlier, rests on the lead screw mechanism, like so. We have the torque arm attached to the lead screw via the mechanism here. Now if you run this torque arm all the way counterclockwise or clockwise, you will engage one of these two kill switches. Now these kill switches, they just cut the power to either the clockwise portion or the counterclockwise portion of the knob. So that let us know the viewing window capabilities or the viewing capabilities of our spectrometer. Another thing that we need to sort out are these handmade slits. Now the reason why we have spectral lines is due to us imaging the slit of the spectrometer. So at first we used the handmade slit on the left here. This handmade slit worked great at first because it enabled us to get an understanding of how the machine worked, how we could find these spectral lines, and what we were looking for. Well, the issue with this homemade slit is that these homemade slits were made with razor blades, and these razor blades are fixed. That means that you cannot adjust the width or the spacing between these slits. It also has the issue of the manufacturing process of these adjustable slits, or the razor blades that make up the adjustable slit. You can see the imperfections in the razor blade edge by viewing the entry slit portion by taking images of the spectral lines. Well, that led me to designing this 3D printed mount in SolidWorks and having the engineering department 3D printing this mount. Well, this 3D printed mount is for this adjustable slit that we bought from Thor Labs. Now, this adjustable slit worked great because now we can have nice, crisp spectral lines without imperfections due to the manufacturing process of the razor blades, but we can also adjust the width of these entry slits. But adding this mount and the adjustable slit added a new issue. Well, adding this adjustable slit removed the imperfections caused by the razor blades, but it changed the distance between our mirror and our entry slit. Now, if you see here on the left, we have an image of the spectral line from the handmade slit, and on the right, we have an image of the adjustable slit. You see that there's a lot of curvature in the lines due to the razor blade. There's a notch here. Well, that is removed when we have this adjustable slit added to the spectrometer. But it widened our spectral lines. This lets us know that we are no longer viewing the focal plane that contains the circle of least confusion, and our mirror needs to be adjusted to view that focal plane. Well, to adjust the mirror, we have the process of adjusting these bolts on the back of the spectrometer. Well, at first, we only decided to adjust these a quarter turn at a time to ensure that we did not lose our spectral lines. Now, I turned them either clockwise or counterclockwise, depending if it widened our spectral lines or narrowed our spectral lines. So, after figuring out which one narrowed our spectral lines, we arrived at this image here. Well, to ensure that it is aligned properly, I decided to take spectral images at the start of the adjustment process and the end of the adjustment process. Well, if you see here, we have really wide spectral lines, and on the right, we have really thin spectral lines. Now, this is what we are looking for because this is imaging the entry slit of our spectrometer or the adjustable slit of our spectrometer. Now, if you notice here at the bottom, these pixel values or the intensity of these pixel values is less than that of the top. Now, this is, from what I understand, due to the Coma Aberration or due to the geometry of the spherical mirror. Now, these crisp spectral lines let us know that, yes, we are in fact imaging the focal plane that contains the circle of least confusion. Also, something important about these spectral lines that we need to know is that we are truly interested in the horizontal information and not the vertical information. So this is kind of what we're going to be aiming for. So using the horizontal intensity information, we want to produce something that is similar to this, the Oriel spectral packet for the neon spectral lines. Well, you see here where we have lit wavelength and the height of these lines depend on the intensity of those lines. And if you look here, we have the neon spectrum. Now we want to be able to find these lines, deduce their wavelengths, calculate their intensity, and produce something like so. Well, to do so, I used Python. So after capturing images of the spectral lines with the EasyCap program, we needed a way of processing them. So I decided to write some code that processed this information. Well, I would like to give a shout out to my friend Clayton for helping me out with syntax errors when the internet would not. I would like to give him credit where credit is due, and I do not want to feel guilty for not mentioning him helping me out. Well, to ensure this code is working properly, I decided to use a test 10 by 10 image. And the reason for that is because our actual images are 880 pixels wide by 643 pixels high. And using a test 10 by 10 image, the output is a little bit more manageable and we can actually see what's going on. So we have on the left here, we have 1 through 7, the pixel columns, and then we have a bright line at the 8th column location, and then we have black pixels at the 9th and 10th column location. Well, Using this image in Python or running this image through my Python code will produce this image here. Well, it produces this matrix here. Well, it produces a matrix of intensity values where we have a scale of black pixels being 0 and white pixels of being 255. So for the test 10 by 10 image, we arrive at this here, where we have the first, second, third, up to the 7th column location being nothing but zeros. And our 8th column has nothing but 255 values. Now this is great because this lets us know that that portion of our code is working properly. So after converting the image to a matrix, the row values of each column in the matrix were summed up to create an array of intensity values. So if you look at equation 8 or the array 8, we have x is equal to the summed value of the row intensity values of the first column. We also have on our second entry here the summed row intensity values of the second column all the way out to C sub n, where n is equal to 1, 2, 3, and so on and so forth. Now for the test 10 by 10 image, we arrived at this array here, where we have our array entry of 1 through 7 being 0, but our 8th entry in our array is a value of 2,550, which is great because this lets us know that we can plot the pixel intensity or the pixel column intensity versus the pixel column location. Now doing so, we arrive at this graph here. Now we want to see a peak, which we do. The unfortunate thing about graphing in Excel is that we have this divot here and also on the right side of the peak. Well, this is just a consequence of graphing in Excel. So using our code with an actual image of a spectral line produces this graph here. So I decided to use the Mercury doublet spectral image in our code to arrive at this graph. We notice at first that it is not equal to 0, or not at 0, like our test image was. Well, this is just due to light pollution and thermal noise within the CCD detector. But the important thing is that we arrive at 2 peaks like so. Now this is a Gaussian style distribution. This is great because this lets us know that we're on the right track. But it also reveals an asymmetry. Now this asymmetry is most likely due to the aberration, the spherical aberration, or the Coma Aberration. Now, to understand the pixel resolution of our spectrometer, I decided to use this in the data in the program Fityk. Well, using the data in the program Fityk enables this graph here, where this lets us see the center of our peak or the location of the center of our peak, as well as the full width half maximum. Now, if you see at the 492 pixel column location, we have a full width half maximum of 3.8. Now, this is letting us know that we have a resolution of 3.8 pixels. So now that we have a pixel resolution of our spectrometer, we need a dispersion of wavelength per, or pixel per wavelength. Well, I decided to use the Mercury doublet, the neon lines at the position of the Mercury doublet, and the sodium doublet. Well, with the Mercury doublet, I arrived at a dispersion of 48.9 pixels per nanometer. With the neon spectral lines, I arrived at a 47.95 pixels per nanometer dispersion. And with the sodium doublet, I arrived at a 46.7 pixel per nanometer dispersion. Now this enabled me to calculate an average dispersion of 47.85 pixels per nanometer. So now that we have an idea about the pixel resolution and the dispersion of our spectrometer, we need to actually correspond the spectral lines to diode readings to get, or we need to correspond diode readings to actual wavelengths. So I decided to find these neon spectral lines, or the wavelengths of these neon spectral lines, using the National Institute of Standards and Technology website or database and the Oriel spectral packet to deduce. And so now that I have data about the wavelengths about these spectral lines, I am able to find these spectral lines, record a dial reading that corresponds to those spectral lines. This will enable me to write a correction curve or see if I need to reanalyze my data. So, like I said earlier, this dial reading is inaccurate and does not correspond to wavelength. And I also noticed that when I found higher wavelengths, they corresponded to lower dial readings. Now, this lets us know that our CCD camera is actually upside down. Now, due to the camera being mounted in the way that it is, I can't just rotate this CCD camera. So this lets us know that we need a correction curve for the dial to correspond to wavelength, as well as for the dial to correspond to the proper wavelength. So once these spectral lines were deduced and the dial readings were recorded for the position of those spectral lines being in the center of the EasyCap software, I decided to plot the dial readings versus the wavelength to give me a distribution. Now the distribution should be linear. Now if any of these line or dots stray away from this line, then that lets me know that they need to be reanalyzed. So plotting the wavelength versus the dial reading, I arrived at this graph here, where we have wavelength on the y-axis and we have dial readings on the x-axis. So if you look in the middle, we have 3 dots that do not lie on our distribution, and we have one over here that does not, as well as one on the top left there. Well, these data points, if they fall off the distribution, like I said earlier, they need to be reanalyzed. So to reanalyze or to predict where these lines are, I decided to use linear interpolation. So linear interpolation requires finding the equation of a trend line, while I used the trend line equation from the Excel graph from the previous plot. Well, using this equation of the trend line, I am able to deduce whether the position should be, or for the position, what the wavelength should be. Now, for the HG point of 540.74 nanometers, I should have a dial reading of 2,340. Now, with that being said, I still have this yet to finish, so I will conclude. So we know that the machine performs well with slight adjustments to the drive shaft and the high-low shift knob. We also know that in recent events that the key that lies within the drive shaft keyway has stopped working properly, so that needs to be replaced. But we also know that the optics are aligned and we are able to view the focal plane that contains the circle of least confusion, so that's great. We also know that our code analyzes the spectral images and produces useful data that we can use. We also realized that we are able to take an old spectrometer, get narrow spectral lines that can be used to get useful information, and this shows that we are able to get this machine to work. It's actually really cool. So a little bit of future work, I need to create a packet that will enable one to go through the step-by-step process of calibrating the machine when they use it. I also need to finish finding spectral lines with the hydrogen spectrum or the hydrogen spectral tube for the calibration of the dial. I also need to take repeated measurements or repeat my measurements to increase the accuracy of our correction curve. And I also need to either fix the astigmatism with the spectrometer or predict how it affects our spectral lines. With that being said, I will show you guys my citations and let you go. Thank you for your time, and I hope you enjoyed the seminar, and I hope you have a great rest of your day.